For the remaining lecture, our main topics are generative model and self-supervised learning. So we will cover autoencoder, variational autoencoder, and GAN, and so on, and also BERT and GPT-2, and some other self-supervised learning method in image classification task. Right. So when you study such algorithm, we usually face some encoder and decoder concept. What is encoder and what is decoder? Encoder, basically, the input of the encoder is image or some text data, sentence, or paragraph. And from the input data, the encoder usually generates some latent variables. Which abstract the hidden information in the input data. And decoder is the reverse process of encoder. So from the latent vector, we generate image or text. Okay, so this is encoder and decoder concept. And usually the dimension of latent variable g is less than or equal to the dimension of original space. Okay, and most of the case, the dimension of latent space is smaller than the dimension of original space. Why? This is very important question. So, of course, there's no perfect answer because a lot of things in deep learning, there's no rigorous proof. But people believe that small dimension of latent space is good for encoding and decoding concept. So to understand such behavior, let's consider this a very simple experiment. What will happen when you randomly generate an image, which means totally pure random variable you put for every pixel. So for instance, if you want to make a new pictures with 64 by 64 pixel size image, for each pixel data, you just randomly generate RGB values in between 0 and 255. Then the result, the outcome, most of the case, 99.999999% of chance, the generated image is purely garbage, nothing meaningful. Just a white noise will appear. So it is entirely not a new picture taken by some people. This is just a noise. Okay, so when you randomly generate an image by some random process, you cannot expect a real like new pictures coming to you, right? Okay, so why such thing happen? Essentially, the input image, for instance, 64 by 64 case, the image belong to very high dimensional space. 64 by 64 image have 64 by 64 by 3 variables, RGB variable for each pixel. So essentially we have 64 by 64 times 3 independent variable that describe the image. But from the huge dimension, the real pictures located very tiny area. Okay, since such high dimensional space is very hard to imagine and very hard to visualize, I will use 3D simple case. Okay, so let's imagine this value is just 3. Of course not, but to make easy. So although the entire space that can make some new image have this cubic shape, so each axis we can have value in between 0 and 255, 0 and 255, and 0 and 255. Among such a huge area, the real pictures will located very tiny sub area. Okay, so people believe that actually we don't need to use such a full dimension. Actually, the pictures located very tiny subspace hidden inside the original very high dimensional space. Okay, let me give you another example. So let's consider simple 2D space. And in 2D space, let's assume that the data located on this line and all the outside line are zero probability. Okay, so data only located on this line and all this outside area is usualless. Okay, since every data inside 2D space belong to this line, we can expect that from this 1D signal value from 0 to 1, there exists some function f 1D space to 2D space such that every point in 1D space map to the line on 2D space. It is possible. There exists such a function f that can describe all the line element from the 1D space value in between 0 and 1. So if the data distributed on very low dimensional subspace or low dimensional manifold, then from very tiny number of latent variable, you can describe all the data using a mapping function f. Okay, this mapping function f is decoder, making real image from latent space. And the inverse function mapping the value on the 2D space to the 1D latent space is called encoder. Right. But yeah, this is very difficult task to find out very nice decoder and encoder. Okay, and there are a bunch of algorithms on how to design the decoder and encoder that can generate very real-like new image or new video or new text. That is GAN and VAE and many following works. Okay, so how can we control the encoder and decoder? I think there are two type of approach. Of course, there are more, but I want to explain two type of approach in this course. The first one is sampling and variational inference technique. And the second one is normalization flow. So what is the sampling and variational inference? So let's reuse the 2D example because this is very easy to visualize. So essentially from our collected data, maybe the collected data located here. So we cannot collect the infinite number of data points. From the collected data, we cannot draw the line directly. Okay, so let's imagine we collect the data and the data looks like this. And we want to design some function that can mapping the latent variable in between 0 and 1 to some very nice line that will describe the data point. So how can find such function f, such decoder f from the data? So this is very difficult task, and sampling based method is this. It's usually very simple. So each time you randomly sample a value from the latent space in between 0 and 1, and then go through the encoder function and see the result. Sample another latent variable using latent variable distribution, and then go through the decoder function and see the result. Repeat this process again and again. Okay. So these blue points are result outcomes from your current encoder. Now you have to measure the distance between the blue data point and the black real data point. In the case, we can use variational inference. So from the sampling, you add some assumption, such like every samples construct some normal distribution, and the outcomes kind of mixture of such normal distribution, and then see the probability of this black dot data point with respect to the mixture of Gaussian constructed from the sampled data point. Of course, the mixture of Gaussian is not generating 1D line, 1D manifold, but it covers entire space. So this is actually the limitation of this sampling and variational inference-based approach. But this is very simple and very easy to compute. So because of the simplicity, I think sampling and variation inference-based approach is the most popular approach in generative model and all the other type of model because of the easiness of training. But there is actually some limitation in that sense. Right. Then what is normalization flow? Essentially, when you have a function f from the same dimension to same dimension, from the Jacobian, you can easily understand the distribution of fg from the latent distribution. Let's say this is latent distribution, and from the latent distribution and the Jacobian of f, you can easily understand the distribution of fg. Okay, I will explain the normalization flow more details in the remaining course.